Okay, now we can continue with the inverse Z transform. So what do we mean by inverse Z transform if we are not able to apply this integral, which is essentially applicable but quite impractical? So instead of that, what we do is if we have some second order, third order, or higher order systems or equations, Z transform formulations, then you have to split it into first order systems, like this example. So let's see this example. X of Z is equal to 3 minus 5 over 6 Z inverse divided by, now this will make a second order system because we will have two coefficients, 1 minus 1 over 4 Z to the minus 1 is one of them, minus 1 is one of them. The other one is 1 minus 1 over 3 . I think this is because of this screen sharing memory leak from the device. It behaves inaccurately, but nevertheless, we will have to continue Z to the minus 1. So as you see, there are two poles, and these two poles are making it a second order system. So we must have two solutions to this, two half exponentials. It's like a to the n u of n or a to the n u of minus n minus 1 types of solutions. So everything depends on how you can split it into first order components, which you should be able to do. And the second one is, of course, the region of convergence, which is given for this one as this, let's say, between 1 over 4 and 1 over 3. It's greater than 1 over 4 and less than 1 over 3. 1 over 4 is one pole, 1 over 3 is the other pole. So you must make a strategy. You should split it into two first order parts. And the solution corresponding with the pole of 1 over 4 should be out of the circle. So it must be a right-hand sided solution. And the one with the pole is equal to 1 over 3 is inside the circle, which must give the left-hand sided solution. Now, I'm not going to the steps of this one. I will just immediately write the result of the first order components like this and this. You should be doing this by saying A over 1 minus 1 over 4 Z inverse plus B over 1 minus 1 over 3 Z inverse, and then find A and B from the equations, which may take some time, of course, but you will get this one. Now, the left-hand side component, this one, has a pole of 1 over 4, which is telling me that Z is greater than 1 over 4, so out of a circle. Therefore, the right-hand sided solution to this one is necessary. X of n is therefore from this, since Z is magnitude of Z, which is the radius, is greater than 1 over 4, the inverse is readily available from the tables as 1 over 4 to the power n un. How about the other one, this one? Now that one in the denominator, in the numerator, sorry, we have a 2, so we have a plus 2 times something, but that something is actually a negative signal, so perhaps I should put a minus sign here. Minus 2 times 1 over 3 to the power n, 1 over, oh my goodness, 1 over 3 to the power n, and the left-hand side is solution, u of minus n minus 1. Yeah, so in fact, that's it. We found the inverse. And this is the approach that you must have. If the region of convergence is given as z is greater than 1 over 3, not this one, but z is greater than 1 over 3, then both of them should be right-hand sided solutions. You must invert each of these components in that way. If z is less than 1 over 4, z is less than 1 over 4 is the region of overall region of convergence. If it's given that way, then both this one and this one should provide left-hand sided solutions, which are all very available in the tables. There is a fourth alternative, which can be like, but it's ridiculous, of course. The region of convergence is an empty set. Then it means it is greater than 1 over 3 and less than 1 over 4. Well, just wait. There seems to be a problem in my connection in the second device, so I will try to join again. Let's see if I can join again. Okay, hopefully it came back. All right. So I hope you can hear me now. I was telling that there are four candidates of the solution for such a system. One of them is this one. The other one is z greater than 1 over 3 in magnitude. The other one is z less than 1 over 4 in magnitude. And the fourth one is z nowhere. That's the empty set for the region of convergence, but that's a nonsense situation because it means that the z transform does not exist. Okay. So this is the way that you should do. You have to convert the z transform into some known z transforms using some of the properties. What are those properties? We will see very quickly now. The alternative way of finding the inverse z transform, you can convert to this form. X of z is equal to the infinite summation, which is the definition of the z transform, by the way, x of n z to the minus n, which is like dot dot plus a z square plus b z plus c plus d z to the minus 1 plus e z to the minus 2 plus f z to the minus 3 plus etc. And this can be readily converted to a a time signal, like over the axis of n. Here the value is c at 0. At minus 1, the value is b. At minus 2, the value is a, and it goes on like that. At 1, it is d. At 2, it's e. At 3, it's f, and it goes on like this. So if you can somehow magically convert your expression into this form, then it's also meaning that it will be meaning that you found the time domain signal in discrete time. Because this also gives us a general way that, in general, delta n plus n0 has a z transform corresponding to z to the n0. Okay, so if you shift to the left by n0, it means you are multiplying your z transform by z to the n0. Or the z transform of the impulse at minus n0 is z to the n0. If n0 is positive, then it means it's a shift to the left. If n0 is negative, that is like delta n minus 3, for example, which will have a z transform of z to the minus 3, that would correspond to a time signal at n is equal to 3. Now, some students, there's a point there where I have to interrupt a little bit and mention about some things. Some students are comfortable with a to the n u of n, like expressions, because they say that it is 1 over 1 minus a z inverse. That's the z transform, okay? But when I say a situation like this, like the thing that I'm going to give you now, tell you now, it's regarding the input-output relation of systems and corresponding exponential input versus exponential output signals. What I'm trying to say is this. How about a to the n? What's the z transform of a to the n? And sometimes the students just say that the z transform is again like 1 over 1 minus a z inverse. But look at it, it's not a to the n times u of n, it is a to the n. There is a very typical exam question that I always ask, which is a question like this. Question tells that there is a system x of z or x of, sorry, it's h because it's a system. Let me write it like this. H of z or h of n, which is the impulse response. H of z is the z transform of the impulse response, which is the system response. There is this system, and the input is 2 to the power n. And the output is blah, blah, I say. And then the students immediately get confused about that. They say that the input is 2 to the n, therefore should I say that x of z is equal to 1 over 1 minus 2z inverse or something, maybe? And then the answer is a big no. It doesn't mean that. What does it mean then? It means the following. First of all, there is, of course, the property that we will use. I will also list out this property, but it's time to mention about it now. X of n convolution h of n will have a z transform of, first of all, x of z times h of z. Just like the Fourier transform, the convolution in time domain will reflect to multiplication in the transform domain. But if the input is 2 to the n, you don't really try to convolve 2 to the n with h of n, or you don't try to take the z transform of 2 to the n and try to multiply it with h of z. Then this, although it's correct, but this thing is becoming invalid. You invalidate this. Instead, you do the following. You think of the following. A to the n, when it goes into a linear and time invariant system, and we're always talking about linear and time invariant systems because we are talking about the Fourier transforms, the Z transforms, the impulse responses. They are all available only for linear and time invariant LTI systems. And for this one, the situation is like this. The output is also a to the n times capital times something, some coefficient, which corresponds to h of z at z is equal to a. This situation was also valid in continuous time like this, e to the j omega t. If it goes in, you remember that the output is also e to the j omega t times h of j omega at omega is equal to, let's call this omega 1. Omega is equal to omega 1. So these are equivalent things. There's also a Laplace counterpart of this one too. Okay, e to the st, that one is e to the st, s1 t goes into a system. The output is e to the s1 t times h of s at s is equal to s1. These are all valid input-output relations. So if the input is 2 to the n, it means that 2 to the n, the input is 2 to the n, the output is that 2 to the n times h of z at z is equal to 2. Let's as h of z is 1 over 1 minus b z inverse. Okay, where b is unknown. Okay, that's how we usually construct questions. And input is 2 to the n. That makes output is equal to 2 to the n times h of z at z is equal to 2, which is 1 over 1 minus b over 2, b times 2 to the minus 1. And the question usually proceeds as follows. I'm giving you a cheating of the exam questions that I most probably will ask right now. So listen very carefully. The question is as follows. This is h of z, where b is unknown. And we apply an input 2 to the n, and we observe that the output is observe output is equal to, let's say, 2 times 2 to the n, which is actually 2 to the n plus 1. Okay, so the input is 2 to the n, the output is 2 to the n plus 1. The question is, what is b? If you don't apply this knowledge, you will never be able to solve the questions. And 99.9% of the students just cannot solve it because they say that h of z is this, input is this, 2 to the n. Therefore, x of z of the input, the z transform of the input is 1 over 1 minus 2z inverse, which is incorrect, very wrong. It's not the z transform of 2 to the n. And they try to multiply them and see if it is equal to 2 to the n plus 1 as an inverse z transform. Complete headache, complete nonsense. You have to do this. You have to say that if the input is 2 to the n, the output is 2 to the n times 1 over 1 minus b over 2. And I'm telling that the output is 2 to the n plus 1, which is 2 times 2 to the n. 2 to the n is here. Therefore, this must be equal to 2. Therefore, b is equal to 1. Because 1 over 1 minus 1 over 2 is equal to 2. This is how you find b, okay? Be careful. A to the n without a u of n or anything is a dangerous signal. You cannot take the z transform of such signals. You can only apply them to LTI systems, which will give you this output. If a to the n goes in, then the output is a to the n times h of z at z is equal to a. That is the formula that you have to always apply. Be careful. I'm warning you because I'm tired of seeing exam results from students who just cannot do that, cannot solve it, because they're not careful enough. In fact, I will be, and I have been talking about this concept from the beginning of the course, but after some time, you forget about it and you focus to some new topics, and you think that the question that I'm asking is related to that new topic, but actually no, as you see, it's related to eigensignals. The input signal is the same as the output times the response. But anyway, so be careful about that. Now, I will show you the last way to convert. So I'm going into the, excuse me, I am going back to this topic here. Can we really convert our Z transform into a normal polynomial like this? And it happens that as long as it's a convergent series, which means you are within the region of convergence, as long as you're in the region of convergence, you can always write any Z function in a Z polynomial form. And the question you have to ask yourselves is, have you ever heard of Taylor series expansion? Because any function has a Taylor series expansion, which is a polynomial expansion. So if you convert from this function, which is non-polynomial, like 1 over 1 minus 1 over 3 Z inverse, it's not a Z polynomial, but you take the Taylor series expansion of that, and it will be a polynomial. And then from that polynomial, from the polynomial to the time signal, it's a piece of cake. It's there already. But it's difficult, usually, but not always. Sometimes it becomes easy, that Taylor expansion, and it's also known as the long division case, which is not really a proper way of taking the Taylor series expansion, but it gives you the Taylor series expansion. If everything is in the form of numerator polynomial divided by denominator polynomial. So if the denominator and the Taylor series expansion is performed by long division, what is that? It's this. X of Z is equal to 1 over 1 minus a Z inverse. Okay, the typical first order thing. Whose inverse Z transform we already know. What was it? It was a to the n u of n. Of course, if Z is greater than a in magnitude, which is the right-hand sided solution. So there can be a left-hand sided solution, but suppose that it's the right-hand sided solution, then how do we make this division? We do this division by literally division. You may remember from primary school second year how to divide, right? You should be able to divide. You divide 1 by 1 minus a Z inverse. And you do this division, literally. Interesting. Actually, maybe I should take this and move it a little bit here, because I will need the space to the left. So how can I do this? First of all, if you are seeking for the right-hand sided solution, it means that you're including the zero term, which is supposed to give you a constant term after the division. So if you start with a constant term at the division, it means you are proceeding towards right-hand side, or the right-hand sided solution, or the solution which will give you negative Z power, Z to the minus 1, Z to the minus 2, Z to the minus 3, etc. That's a case when Z is greater than A. So the question I start is, how many 1 minus AZ inverses are there inside 1? Okay, I'm dividing. So how many of this will fit into this? That is the question. And I start by saying one of them will fit, because if I do it, it means I will subtract from 1 this. And since Z is greater than A, 1 minus AZ inverse is actually less than 1, and therefore this will give me a positive result after the subtraction, and the subtraction result will be this one and this one will cancel one another, negative of minus AZ inverse, and that is AZ inverse. AZ inverse is left, is a remainder. Then I will continue. Then the question is, how many of these are there inside a Z inverse? Now that's the critical thing. And if you understand this step, the rest of the steps will be easy for you. And the answer is for this one is a Z inverse. Many of these terms exist inside a Z inverse. Why? Because if I multiply this by AZ inverse and subtract from this, I will get something else. What is AZ inverse times 1 minus AZ inverse? It is AZ inverse minus A square Z to the minus 2. I subtract them. Again, AZ inverses cancel, and I am left with A square Z to the minus 2. And I repeat the question, how many of 1 minus AZ inverses are there inside A square Z to the minus 2? And the answer is A square Z to the minus 2. Oh my God. A square Z to the minus 2. If I multiply 1 minus AZ inverse with this new term, the result will be A square Z to the minus 2, which will be the canceling part, as you have noticed already, minus A cube Z to the minus 3. I subtract. Again, these will cancel, and the result will be A cube Z to the minus 3. So the next one is A to the 3 Z to the minus 3, which will give you A to the 3 Z to the minus 3 minus A to the 4 Z to the minus 4. You subtract them, and then these will cancel, and it goes on like this. So let's make an inspection of these terms. Of course, it goes on. But we can make an extrapolation. It's easy to guess the pattern here. It's 1 plus AZ to the minus 1 plus A square Z to the minus 2 plus A cube Z to the minus 3 plus A to the 4 Z to the minus 4, right? It all goes on like that. And how can I write it in a compact form? So x of n is equal to, first of all, 0 for n less than 0. It's equal to 1 for n is equal to 1. It's equal to a for n is equal to 2. Excuse me. 1 for n is equal to 0. A for n is equal to 1. A square for n is equal to 2. A cube for n is equal to 3. And going on like this. So now can I write it in a compact form? Sorry. Yes, of course. X of n is equal to a to the power n for positive n only, of course. So for positive n, it means it's a to the power n times u of n. There you go. We found it. It seems to be a very long sequence, but the mathematical expression, compact expression of that long mathematical, long sample by sample values will correspond to x of n is equal to a to the n u of n. So we found it. We found it with the prejudice that z is greater than a, or the right-hand solution I'm looking for. Therefore, I'm trying to deliberately obtain terms in this form, az inverse, for example, or a squared z to the minus 2, a to the 3 z to the minus 3, right? If I'm looking for the solution for the same thing, so the question is, the new example question is same, but z in magnitude is less than a in magnitude. So we again divide 1 by 1 minus a z inverse again. But this time I want to proceed the result to positive z powers, something times z to the positive. And that first choice is a to the minus 1 z. a to the minus 1z. Because when I multiply the top with this a to the minus 1z and I put a negative sign here, a minus sign here, this times this time will give me 1. And I want to obtain a 1 because I want it to cancel after the subtraction. So, or maybe it's wiser for you to think of it like this. I will erase everything and I will write it in an alternative form. It's the same division I'm making. 1 over minus a z inverse plus 1. This is the thing that I'm dividing. I'm just doing the trick that I am trying to obtain 1 from the first term here. So a to the minus 1 minus a to the minus 1 z is my first candidate. And when I multiply it with the top term, it will give me 1 it will give me 1 minus a to the minus 1z. Okay, that is the multiplication. And I subtract as usual. 1 here and 1 here will cancel, and I will obtain a to the minus 1 z. And now I will obtain another term with which I want to obtain a term here with which when I multiply with minus a z inverse, it will give me a to the minus 1 z. What is that? That is minus a to the minus 2 z squared. Because when I multiply this with this, it will give me this. Okay, that's how I adjust this value. And that is a to the minus 1 z minus a to the minus 2 z squared. And I subtract it. And in the subtraction again, we are seeking for a cancellation of the first terms. And therefore, I have a to the minus 2 z squared. So I have to multiply it by a to the minus 3 z cube. And after the multiplication, it's going to give me a to the minus 2 z squared minus a to the minus 3 z cube. Subtraction. These will cancel, and the result will be a to the minus 3 z cube. Z cube, it must be. Therefore, it goes on like this, minus a to the minus 4z to the 4 minus blah, blah. So that is the z transform with positive z powers and with negative or minusly signed coefficients, which can be written as x of n is equal to, when n is equal to minus 1, when n is equal to minus 1, that is z to the 1. The coefficient is minus a inverse. So minus a inverse when n is equal to minus 1. It is minus a to the minus 2 when n is equal to minus 2. It's equal to minus a to the minus 3 when n is equal to minus 3, etc. And it goes on like that. So how can I just express this? And when n is equal to 0 or positive, the values are equal to 0. So I can see that x of n is equal to minus a to the power n. For n is equal to minus 3, for example, it will give me minus a to the minus 3. For n is equal to minus 3. But it must be valid only for the negative n integers. So I must multiply by u of minus n minus 1. And I put it in a box and say that this is the inverse Z transform. This is called long division. These long division examples are available for polynomial numerator divided by polynomial denominators, and you have to be careful about where to proceed, which direction to proceed. Are you proceeding to z squared, z cubed, z to the 4, or are you proceeding to z to the -1, z to the -2, z to the -3, etc.? One of them, the z to the minus things, will correspond to right-hand sided solution. Z to the plus powers will correspond to negative sided, left-hand sided solutions. But as you see, we did it just by dividing, and the rules are simple, basic, fundamental division rules. The next and the last example for today is the Taylor series expansion, not by long division, but using Taylor series, exactly. X of z is equal to logarithm of 1 plus a z inverse. And this is an awesome z transform. It's such an awesome z transform that sometimes it really exists inside the tables of typical z transform pairs in the z transform domain. Logarithm of this. Is there a pole? Interestingly, yes, there is a pole of this one, and it's at z is equal to a, because when z is equal to a, actually z is equal to minus a, excuse me. When z is equal to minus a, z inverse will be -1 over a, times a will be -1, and 1 minus 1 will be 0, and logarithm of 0 is -infinity. So it's a divergence point. It's a singularity. Therefore, z is equal to minus a is a pole. Let's indicate it. Z is equal to minus a is a pole. And for the z transform to be right-hand sided, we must have the radius greater than the magnitude or the absolute value of a. This a can be positive or negative, and negative of it can also be positive or negative. So we don't care about that. It's only the radius, and the radius is the absolute value of a. Greater than that is the region of convergence, which is imposing us that we need to find the right-hand sided solution, inversion of this z transform. But what is it? If this is the case, if z is greater than a z inverse, excuse me, then a z inverse in magnitude becomes less than 1. So this term in magnitude, it's less than 1. It's like logarithm of 1 plus theta. And we have to look for the Taylor series expansion of logarithm of 1 plus theta for small theta, for theta less than 1, in other words. What is the Taylor series expansion? This, I have to confess that I cannot ask you as an exam question without giving you the Taylor series expansion formula. It's not because I cannot expect you to remember it. It's usually at the backside of appendices of calculus books. But in examinations, we do provide you with the Taylor series expansion formula that you need to apply. And that formula for our case is this: logarithm of 1 plus v, as calculus books usually do, is equal to summation from 1 to infinity -1 to the power n plus 1 v to the n over n. This is the Taylor series expansion formula for logarithm of 1 plus v. And since v is equal to az inverse, you just need to put it that way. Of course, this is valid for magnitude of v less than 1, and that is the case for you as well. So x of z, therefore, it's not a therefore, it's equals. Therefore, x of z is equal to the same summation, and from 1 to infinity, the same things, -1 to the power n plus 1, and v is equal to az inverse, so v to the n is equal to a to the n, z to the minus n, right, divided by n. This is the polynomial approximation. As n goes to infinity, it converges. the polynomial approximation of logarithm of 1 plus AZ inverse. Now, from here, can you tell me what is x of n? X of n is anything that multiplies z to the minus n, right? Because that's what it is. It's here. This part, everything that multiplies z to the minus n in the z transformation summation, they are the coefficients of x of n. So x of n is equal to that, which is minus 1 to the power n plus 1, a to the n over n. That's it. But this is only valid for positive n's, and even even n is equal to 0 is not included here, because there is a division by n, so n is equal to 0 is a singularity, and we can see that, clearly see that the summation actually starts from 1. So this expression of z transform, x of n z to the minus n, is valid from 1 to infinity. So be careful about how to write the right-hand side of this. I will do it in two ways. This is the result for n greater than 0, including 1, and it's equal to 0 when n is less than or equal to 0, including 0, unfortunately. You can write it like this, or if you are a better signal processing student, you can also write it as minus 1 to the power n plus 1, a to the n over n times u of n minus 1, which is one shifted version of u of n to the right-hand side, and it forces n to start from 1. So let's write it like that then. This is the best expression that we may have. Very awkward, very interesting result. And conversely, if I say that x of n is equal to this, what is the z transform of it? That would be a very difficult question, but eventually, if you can combine it in a simplified form, you have to say that x of z is therefore logarithm of 1 plus a z inverse. That's truly strange. Now, if I were the student, if I were in your shoes, then I would look at some examples of other functions which have similar Taylor expansion formulas, like maybe a cosine, maybe a sine, right? Logarithm is one of them, but I think sinusoids are the next candidates, which can be converted into polynomial format using Taylor expansion like this one. But of course, as I say, if I attempt to ask this kind of a question, I will definitely provide you with the hint saying that logarithm of 1 plus v is this for v less than 1. So I will give you this formula in the examination if I ask this kind of a question, at least. Okay, so our time is now running out. I will have to stop. If you have any questions, we can address a few questions, or else I will stop it and I will say see you next year, which is the uncanny joke. But next year, first Monday at 9 o'clock, we do have a class. It means on Monday and Wednesday, we will have to wrap up everything remaining from the Z transform, which will be definitely included in your final. So next week we have classes, same place, same hours. Now, is there a question? I will give you a few seconds if you have any questions. If you don't, I don't encounter any questions, then see you next week. I wish you a happy new year, successful, healthy, and all that, and say bye-bye.